Welcome to the Deep Dive, the show that cuts through the noise and, well, delivers genuine insights directly to you. Today, we're taking a serious look at Go, often called Golang. It's a language that has really reshaped how we think about building scalable, high performance systems. Forget the basics you might have picked up. Our mission today is to go deep. We're unearthing 12 advanced features that make Go not just good, but exceptionally suitable for high performance concurrent applications. Our sources are packed with details, and we're here to distill those critical nuggets of knowledge, giving you a shortcut to truly understanding Go's power and its, unique approach to modern software engineering.
And that's precisely the point, isn't it? These aren't just isolated language constructs. When you look at these features together, they reveal a kind of cohesive design philosophy. In today's landscape, building systems that can handle immense loads, distribute work efficiently, and remain resilient in the face of failure is paramount. Go provides a toolkit deliberately crafted to address those very challenges, often with surprising elegance, and understanding these advanced features is really key to unlocking that potential.
Absolutely. So let's jump right in by unpacking Go's core philosophy around concurrency. This is really where Go, well, carved its niche, and it all starts with Go routines. For an advanced developer, the crucial insight isn't just that they're lightweight, it's how lightweight they are. We're talking about just a few kilobytes of stack space managed by the Go runtime, not the operating system. This allows you to spin up not just dozens, but hundreds of thousands of concurrent operations without the crushing overhead or context switching costs of traditional OS threads. It's an abstraction that fundamentally changes what's feasible in a single process. And when you create one with GoSum function, that simple keyword completely abstracts away the complexity of thread management. It frees you to think about concurrent tasks rather than low-level threading primitives.
Exactly. The real power here is that Go embraces the communicating sequential processes, or CSP model, from the ground up. It makes concurrency a first-class citizen rather than, say, an afterthought bolted onto the language. This dramatically simplifies the mental model required for concurrent programming. For developers accustomed to mutexes, locks, and shared memory, Go routines offer a fundamentally less error-prone way to achieve parallel execution.
That's a huge shift in paradigm, a big deal. But Go routines are only half the story, right? For them to work together safely, they need to communicate. That's where channels come in. Rather than shared memory, Go champions explicit, synchronized communication via channels. Think of them as typed conduits that allow Go routines to send and receive values. The critical takeaway here is that channels provide a safe, synchronized way to pass ownership of data between concurrent tasks. This virtually eliminates the race conditions that plague shared memory concurrency. And while many are familiar with Dretch, make chan int, where you send data with gred-42 and receive with val, the distinction between unbuffered and buffered channels also dictates communication patterns. Unbuffered channels act as rendezvous points, forcing both sender and receiver to be ready, which is ideal for tight synchronization.
Right.
Buffered channels, on the other hand, provide a queue, allowing asynchronous sends up to the buffer capacity, which can be great for throughput when you can tolerate a slight delay.
It's all about explicit coordination. If we connect this to the bigger picture, this Gortine and channel model allows you to build sophisticated data pipelines and workflow orchestrations that are both performant and incredibly robust. You're defining clear boundaries and communication protocols between your concurrent tasks, making reasoning about complex systems much, much easier. The Go runtime itself handles the scheduling and multiplexing of Go routines onto OS threads, so you, as the developer, are focused on the logic of your concurrent operations.
Okay, that makes sense. And for orchestrating those operations across multiple channels, you need the select statement. This is Go's tool for non-blocking I/O and multiplexing operations across several communication channels. The insight here is its ability to elegantly wait on multiple channel operations and proceed with whichever one is ready first. It's not just a switch statement for channels, it's a powerful mechanism for building responsive services that react to various inputs or events without blocking the entire process. You'll see patterns like select case val, nesh1 case val, neshable, neshable default, for handling incoming data, timeouts, or even graceful shutdowns. It's a core component for truly dynamic concurrency control.
Indeed. It's critical for building highly responsive, event-driven architectures. The select statement enables Go routines to perform what's known as non-blocking reads on multiple channels, which is fundamental for building things like network servers that can handle many client connections simultaneously, or state machines that react to external triggers. Without it, managing these scenarios would quickly devolve into complex polling loops, or, well, callback hell.
Right, yeah. Callback hell. Nobody wants that. Okay, moving on. Let's explore features that make Go code robust, clear, and exceptionally maintainable. One such kind of unsung hero is the defer statement. It's a remarkably simple construct that schedules a function call to be executed just before the surrounding function returns. The true power for an advanced developer is the ironclad guarantee it provides for resource cleanup, whether a function completes successfully, returns an error, or even panics. Defer ensures that actions like closing files, unlocking mutexes, or tearing down network connections always happen. This dramatically reduces boilerplate and eliminates entire classes of resource leakage bugs, and the LIFO order, last in, first out, of deferred calls means the cleanup sequence is correct too.
Like defer fmt.println last, then defer fmt.println first prints first, then last.
Exactly. It's vital for nested resource acquisition. It's just a clean, deterministic way to manage resources.
Absolutely. The defer statement is a prime example of Go's philosophy of empowering developers to write correct code by default. It makes resource management explicit and, well, foolproof. Think of the try-finally blocks or REII patterns in other languages. Defer provides a far more lightweight and readable alternative that consistently gets the job done without complex nesting.
Makes sense. Okay, next we dive into Go's take on polymorphism. Interfaces. Unlike many other languages, Go interfaces define a set of method signatures without any implementation, and critically types implicitly satisfy them. This duck typing approach means any concrete type that implements all the methods of an interface automatically fulfills that interface. There's no explicit implements keyword. The insight here is profound. It promotes loose coupling by allowing you to define contracts based purely on behavior. This makes code vastly more flexible, testable, and adaptable to change. You can swap out implementations of an interface without modifying the consuming code, which is invaluable for mocking in tests or evolving system components. For instance, if you define type speaker interface, a dog struct with a speak method is simply a speaker. Polymorphism without class hierarchies. Pretty neat.
Very flexible.
And speaking of how Go structures types, it deliberately forgoes classical inheritance. Instead, it offers struct embedding. This mechanism allows one struct to include another, effectively promoting composition over inheritance. You're building complex types by composing simpler ones, rather than inheriting their behavior. For example, embedding an animal struct within a dog struct, type dog animal, allows a dspeak call to delegate to the embedded animal speak method. But dog can also define its own speak method to override or extend that behavior. It's a clean, explicit way to reuse code and construct types, avoiding the infamous diamond problem and rigid class hierarchies found in other languages.
This raises an important question, though. Why does Go favor composition and implicit interfaces so strongly? It's a fundamental design choice that emphasizes flexibility, testability, and avoiding tight coupling. Explicit inheritance can often lead to what we call fragile base class problems, where changes to a parent class unintentionally break many child classes. Go's approach encourages you to design systems where components interact via well-defined interfaces, where complex types are built from distinct reusable parts. This significantly improves maintainability and adaptability, especially as projects scale and requirements evolve.
That truly highlights Go's practical mindset. All right, now let's look at some features that give Go programs incredible flexibility and adaptability at runtime. First up, reflection. Go's reflection capabilities, primarily through the Reflect package, allow programs to inspect and manipulate objects at runtime. This means your code can, in essence, look at itself, determining a variable's type, its underlying value, and even modifying that value programmatically. Tools like Reflect, Type, and Reflect value provide granular access. The critical nuance here is that to modify a value using reflection, you must always pass a pointer to grant modification access, as in reflect.valueofx.elem setfloat 7.1. This isn't just a party trick. Reflection is vital for building powerful generic frameworks. Think JSON marshalling, ORMs, dependency injection containers, where type information isn't known at compile time. However, it comes with a performance overhead and bypasses compile time type safety, so it's a tool for specific advanced scenarios. Use with care. It's a double-edged sword, absolutely. Reflection provides a dynamic escape hatch when truly needed, offering incredible power for metaprogramming. But as you mentioned, it's generally best reserved for infrastructure-level code rather than everyday application logic, precisely because it sacrifices some of Go's hallmark type safety and performance guarantees.
That balance is key. Then we have generics, introduced in Go 1.12. This was a carefully considered addition, addressing a long-standing desire for more flexible and reusable code without sacrificing type safety or adding excessive complexity to the language. The benefit is significant. You can write functions and data structures that operate on various types while still maintaining compile time type checking. No more resorting to interface and costly runtime type assertions for common patterns like collections. So func print t, any, sufs spell t, allows t to be any type, providing a type-safe generic print function. And type pair t, any struct, verse second t lets you define generic data structures. Generics enable safer, more performant, and more readable code in common patterns, reducing boilerplate across your code base.
Generics fundamentally change the landscape for building reusable libraries in Go. Before 1.18, many common data structures or utility functions either had to be written specifically for each type or rely on interface with runtime type assertions, which could be error-prone and, frankly, slower. Generics provide that critical balance, allowing developers to write truly type-safe and performant polymorphic code. The insight here is the careful, sort of conservative approach Go took to introducing them, prioritizing simplicity and compile time performance.
Makes sense. And finally in this section, let's talk about higher-order functions and closures. Go treats functions as first-class citizens, which is a powerful concept. This means functions can be passed as arguments, returned from other functions, and even stored in variables. This enables incredibly flexible and expressive API design, supporting functional programming paradigms where appropriate. Closures are a natural extension of this. They are functions that capture and retain access to variables from their enclosing scope even after that outer scope has finished executing. This allows you to create functions with private state. For example, an adder function could return two different closures, pose and neg, each maintaining its own separate sum variable. This is incredibly powerful for encapsulating state, creating factory functions, or implementing callback patterns.
The ability to treat functions as values, combined with closures, empowers developers to write highly modular and adaptable code. You can dynamically create and modify behavior at runtime or easily customize algorithms without needing complex class hierarchies. This is vital for building flexible configuration systems, event handlers, or even internal DSLs within your Go applications. It often leads to more concise and readable solutions for complex problems.
So we've seen how these features give Go programs incredible flexibility. Let's shift gears now to practical management and low-level control. Go handles memory management through its automatic garbage collection, or GC, system. The insight here is that Go's GC is specifically designed for server-side workloads, prioritizing low-latency pauses rather than simply maximizing throughput. This means developers are freed from the error-prone manual memory allocation and deallocation, allowing them to focus on business logic while the GC efficiently reclaims memory with minimal impact on application responsiveness. While mostly hands-off, the runtime package does offer some knobs for advanced tuning, such as runtime.gc, for manual triggers and very specific high-demand scenarios. But for the vast majority of applications, Go's GC is highly optimized and requires little intervention. It just works.
It's a crucial component for building reliable, long-running services. The engineering effort put into Go's GC means that even under heavy load, pause times are typically in the order of microseconds, not milliseconds or seconds. This makes Go an excellent choice for latency-sensitive applications where consistent performance is key, preventing the kinds of unexpected stalls you might encounter in other managed runtimes.
Okay. Building on our concurrency primitives, let's look at a practical application. The worker pool pattern. This is a common and incredibly effective way to manage and process a large number of tasks concurrently, optimizing resource utilization and enhancing throughput. The insight here is how elegantly Go's goroutines and channels combine to implement this. You create a fixed number of worker goroutines that continuously listen on a jobs channel for new tasks. Once a task is processed, the result is sent back on a results channel. Async wait group then allows the main goroutine to wait for all tasks and workers to complete, ensuring graceful shutdown. It's a robust, scalable, and idiomatic pattern for managing parallel computation, effectively throttling the number of concurrent operations to prevent resource exhaustion.
This is a perfect example of Go's concurrency model in action, moving from basic primitives to powerful architectural patterns. Worker pools allow you to control resource consumption. You're not spinning up a Go routine for every single task, potentially overwhelming your system. Instead, you're efficiently utilizing a predefined set of resources. This is foundational for building scalable microservices, background processing systems, and data processing pipelines.
Very practical. Next up, the context package. For any developer building robust distributed Go applications, the context package is indispensable. Its primary role is to manage coroutine lifecycles and propagate request-scoped values. The core insight is its ability to provide a consistent, structured way to handle cancellation, timeouts, and crucial request-specific data across a chain of coroutines, especially in long-running operations like network requests, database queries, or microservice calls. Using context with timeout allows you to set a deadline for an operation, and coroutines down the call chain can check TDX, done, to gracefully stop their work if the context is canceled or times out. This avoids wasted computation and prevents resource leaks, which is absolutely critical in microservice architectures for preventing cascading failures.
The context package elevates error handling and resource management to an architectural level. It standardizes how you propagate operational concerns, like deadlines and cancellation signals throughout complex systems, ensuring that even deeply nested calls can respond appropriately. It's really a non-negotiable tool for building production-grade, resilient Go applications.
Agreed. Then we have custom error types. Go famously champions explicit error handling through return error values, favoring clarity over exceptions. The advanced insight here is that you're not limited to simple string errors. Developers can define custom error types to provide rich, structured, and programmatic error information. By defining type myErrorStruct, MSG_string, and giving it an error method, you allow callers to not only check for the presence of an error, but also to introspect it. You can check error, myError, to see if it's a specific type of error, and then access its code or MSG fields to handle different error conditions gracefully. This leads to more precise, maintainable, and robust error handling logic than simply parsing error strings.
Custom error types are fundamental for building expressive and resilient APIs. They allow you to differentiate between transient network errors, validation failures, authorization issues, you name it, and then respond programmatically. This reduces the cognitive load on callers of your functions, enabling them to handle errors with a fine-grained approach, which is critical in robust system design.
Excellent point. Finally, for those rare moments requiring absolute low-level control, Go offers the Syscall package. This package provides direct access to operating system primitives. The crucial insight is that Syscall serves as an escape hatch. For scenarios where Go's standard library abstractions simply aren't sufficient, such as highly optimized network programming, custom signal handling, or direct interaction with specific hardware registers. For instance, Syscall.ename allows direct retrieval of system information. However, this power comes with immense responsibility. It's important to use it judiciously and with extreme caution, as improper use can indeed lead to system instability, security vulnerabilities, and platform-specific code. For most operations, Go's robust standard library provides safer, more portable, and equally performant alternatives. This is a tool you keep in your back pocket for truly exceptional circumstances.
That's a vital distinction. The Syscall package is there for the very specific, performance-critical or hardware interfacing scenarios where you need to bypass higher-level abstractions. But Go's philosophy is to provide robust, well-tested, standard library functions first. The presence of Syscall simply means Go can go to the metal when needed without being forced to, offering a pragmatic balance between high-level productivity and low-level control.
Phew! What an incredible journey we've had today, diving deep into Go's advanced features, from its innovative concurrency model with coroutines, channels, and select, through structuring robust and maintainable code with defer, interfaces, and embedding, to its dynamic capabilities like reflection, generics, and closures, and finally, practical system controls like garbage collection, worker pools, context, custom error types, and even the low-level Syscall package. We've truly seen how these features, when mastered, empower developers to write efficient, scalable, and maintainable code, harnessing the full potential of Go to build robust and high-performance applications that meet the rigorous demands of modern software.
Go's design philosophy is clearly evident in each of these advanced features. A strong emphasis on simplicity and primitives, explicit design for clarity, and powerful abstractions where they make sense. Consider how this approach, balancing ease of use with deep control and a deliberate avoidance of complexity challenges conventional wisdom in programming. How does Go make you rethink your assumptions about what a modern systems language should provide, and maybe just as importantly, what it should not?
That's a fantastic question to ponder long after our deep dive ends. Thank you for joining us today. We hope you feel much more informed and perhaps even inspired to explore these fascinating topics further on your own. Until next time, keep learning.